my name is Chris Harris and I'm from Allery Chemistry, and welcome to this video on AQA, properties of period 3 elements and their oxides. So this video is dedicated to AQA, and so if you are studying AQA chemistry, then this video is particularly for you, I should say, mainly because everything in here is specifically tailored for AQA, and it doesn't have any more information that you need to know, and it doesn't have any information here where you might be thinking, do I need to know this? Is this on the specification? Well, everything in here is actually dedicated to AQA, so this is perfect for you. And in fact, there is a full range of AQA videos as well on Allery Chemistry YouTube channel. So there is year 1 and year 2 content, so as well as some whiteboard videos as well, looking at some whiteboard tutorials, looking at some specific areas of chemistry, and also there's some exam technique walkthroughs as well. So all I ask is that you hit the subscribe button, because they're all for free, and as long as people keep subscribing and watching, then I will keep making the videos. So this is dedicated to AQA. If you want this PowerPoint, this is just a PowerPoint slide that I've made as part of revision resources. Then if you just click on the link below in the description box, you'll be able to get a hold of them there. You'll be able to purchase them. They are really good value for money, great value for money in terms of the way you can use them. So for example, you use them on the tablet, you can use them on the smartphone, on the move, you can print them off. I know some people do print them off and use them as revision notes. So they're quite versatile, so there's quite a lot that you can do with this. So click on the link and you'll be able to get a hold of them there. Okay, so like I say, this video is dedicated to AQA, and it meets the specification as you can see on there. So it meets all these different points here. So it's quite a short topic, this one. There's a lot of trends here and a lot of chemical reactions as well. So there's quite a bit on that, but relatively speaking, it's quite a short topic. Okay, so let's have a look at, obviously this topic's all on group 2. Okay, so we're going to look at some comparisons here. And this is going to look at sodium, which is in group 1, is more reactive than magnesium, which is in group 2. And when they lose electrons, they form an Na plus and Mg2 plus ion respectively. Okay, so that's what you would expect with a lot of metals, to be honest, where they lose electrons to form 2 plus charges. And so sodium is actually more reactive than magnesium, as the amount of energy required to remove an electron from sodium is lower than it is to remove 2 from magnesium, which kind of sounds obvious because you're only taking 1 electron away from sodium, whereas you have to take 2 away from magnesium. So that means obviously you're going to need a little bit more energy because you're removing 2 of them instead of 1. And so more energy, like I say, is required for magnesium to react. So this has quite an important point when we're looking at reactivity. So let's look at sodium first. So sodium actually reacts vigorously with cold water, and it forms a ball, and it starts fizzing because we're producing hydrogen gas. Now we can actually test that hydrogen gas by using a lighted splint, and it will produce that squeaky pop that you might have seen already in your lessons, or your lectures, or if you go to school or college, or you can see it on the video. Of course, you can see there's loads of YouTube videos showing the reaction of sodium reacting with water. It also produces an alkaline solution, which is sodium hydroxide. So if you put litmus paper in there, or universal indicator, whatever you're going to do, it would show or indicate for an alkaline solution. So the reaction is this. So it's sodium reacting with water. It will form sodium hydroxide and water. So you need to be aware of them reactions to do with sodium. Okay, so let's compare this with magnesium. Now magnesium does react with water, but it reacts incredibly slowly with water, and it forms a weak alkaline solution of magnesium hydroxide. So it's still forming an alkaline solution, but it's weak because it's sparingly soluble, so it doesn't really dissolve very well in water. So we don't have many OH minus ions. And the reason why we don't have many OH minus ions is because of it doesn't dissociate that well in water. So equilibrium lies well over to the left hand side, in other words. So it doesn't dissociate very well when it's dissolved in solution. So therefore, it's a weak alkaline solution. So the reaction here. There's actually 2 different things to mention here. So this is magnesium reacting with water. That will form magnesium hydroxide and hydrogen. However, it does react much faster when it's reacted with steam. and actually it doesn't produce a hydroxide when it reacts with steam. It actually produces an oxide. That's really, really important. So when you react it with steam, so when you're looking at the question, make sure you're familiar with what they're after. If they're asking for it with steam, then you produce magnesium oxide. If it's with water, it's obviously a hydroxide, which is there. Okay, so don't get them too mixed up. So let's have a look at the reaction of that. There it is. So magnesium reacting with water, as you can see, it's a gas, so that means that steam will produce magnesium oxide and hydrogen. So just make sure you're looking at the state symbols here, because that's going to have a big impact on what product you're making. Okay, so let's have a look at the reaction with water. Now these period 3 elements, sorry, so this is period 3. I did say group 2, didn't I, before? So I apologise for that. Obviously, this is group 3, period 3. Sorry, these are period 3 elements. I'm just not switched on today. So yes, so these are period 3 elements. So of course, sodium would be included in period 3. So I apologise for that before. Okay, so period 3 elements, they react with oxygen to form oxides. Okay, fairly straightforward this little bit here. But with the exception is sulfur, because that forms sulfur dioxide with an oxidation number of +4. And with a higher temperature and catalyst, SO3 can be made into an oxidation number of +6. So let's have a look at what we actually form here. So we've got sodium reacting with half oxygen will form 2 lots of sodium oxide, which is our solid, and that forms sodium oxide. Magnesium reacts with oxygen to form magnesium oxide, as you can see on there. Aluminium reacts with oxygen to form aluminium oxide, Al2O3. As you can see, silicon reacts with oxygen to form silicon dioxide, SiO2. Phosphorus reacts with the oxygen to form P4. Notice phosphorus, is actually in the formation of P4. Okay, so that's P4, and that forms P4O10, which is phosphorus 5 oxide. And then obviously sulfur forms sulfur dioxide, which has the oxidation number +4. But with a higher temperature and catalyst, SO3 can actually be made as well. So it has various different oxidation states with regards to, various different oxidation states with regards to oxides for sulfur. All the other ones form pretty much straight up oxides. These are the ones that you need to know, but just be aware that sulfur is a slight exception here, because actually it forms SO3. It can form SO3 as well if it's at a higher temperature. Just be aware of that. Okay, so let's have a look at some different types of reactions here, and what we're going to look at is the formula of the substance that we're using. So in this case, we're going to react it with sodium, and when we react it with air, how does it actually react? So we'll look at sodium first. So sodium is sodium oxide, and that reacts really quickly with air. As you may have seen, sodium, if you put that out in the atmosphere, then it does react actually quite vigorously. Well, not vigorously, but it does react with oxygen, so it tarnishes on the edge. So it does actually react quite well with that. And likewise with magnesium, that's exactly the same as well. So magnesium reacting with air forms magnesium oxide. That's a very fast reaction as well. Now, aluminium oxide. So this is obviously when we're heating it up. Aluminium oxide is slow, but it's fast if it's powdered. If we react it with air, which is because it's got a larger surface area, so the reaction can happen quicker if it's got a larger surface area. So remember that from your rate of reactions topic. Sulfur dioxide is slow. It reacts slowly with air. Phosphorus, it spontaneously combusts. You've got to be very, very careful with phosphorus. Just a small amount of heat and that will completely go up in smoke. And then obviously our sulfur dioxide, we'll just look at the dioxide version here. Sulfur dioxide actually burns steadily in oxygen. Okay, so we're now going to look at the structure and bonding of some of these period 3 elements. Okay, so actually the structure and bonding of group 3 oxides that affects their melting points, and we can plot these on a graph and have a look. So here they are all here. So you can see there's a melting points of group 3 oxides, and what I've done is I've plotted each of the points on there, so you can see what we've got. Now you can see here this is slightly hidden. There's a point behind there. I'll get that amended. I'll just stretch that out over here. But effectively, you can see the melting points of your group 3 oxides that are all listed here. Okay, so they've all got different melting points, as you can see, and we need to try and attribute their melting points with their properties, effectively their physical properties, their bonding, for example, the types of bond. So let's have a look. So the first three, which is sodium oxide, magnesium oxide, and aluminium oxide, so these all have high melting points as they form giant ionic lattices. So remember, this is a metal and non-metals, so they're going to form ionic compounds, and the ionic compounds, they form a giant ionic lattices. Okay, so substances which are giant ionic have really high melting points because you've got lots of strong electrostatic forces between the oppositely charged ions that make that big structure there, the giant ionic structure. So giant ionic lattices, they have lots of, like I say, strong electrostatic attractive forces, requires loads of energy to break them, and this is why they have high melting points. Okay, so let's have a look at the next one. So let's have a look at magnesium oxide out of all these three. So magnesium oxide has a higher melting point than sodium oxide. And this is because magnesium forms 2+ ions, sodium only forms 1+. And so remember, these because they've got a bigger charge on them, they're going to have a bigger electrostatic attraction between the ions because they've got a higher charge density. So there's more charge per size of the ion. Okay, the ion is very similar to sodium. There isn't a significant difference in the size, but the charge is bigger, so the charge density is obviously much greater. So that's the key thing here. So aluminium oxide has a slightly lower melting point than magnesium oxide, as the aluminium 3+ ions distort the electron cloud. Okay, so that electron cloud of oxygen is slightly distorted. This means you have a little bit of covalent character in here. The reason why I've got some distortion, just before I move on to the next part, but the reason why you have distortion is because your aluminium has got a 3+ charge. That's quite a significant charge, and that's going to pull the electrons from the oxygen towards itself, which is typical of some kind of covalent character. Okay, so this means because there's some covalent character in there, and it's not a purely ionic or it's not, doesn't have more ionic characteristics, and this means less energy is required to break the bonds. So that's why aluminium oxide, although it's classed as an ionic compound, it does have some covalent character in there as well, and this means that obviously less energy is required to break the bonds in aluminium oxide. Okay, right, so let's have a look at silicon dioxide now. Let's move on to this one. So silicon dioxide actually has a higher melting point than the rest of the non-metal oxides. As you can see, it's just tucked away. It's just tucked away around here. But silicon, phosphorus, and sulfur, these are all classed as non-metals. We can see normally our non-metals, non-metal oxides have low melting points, you can see there, but silicon dioxide kind of deviates away from this. The reason why is silicon dioxide actually forms a macromolecular structure. This is a covalent, giant covalent structure. It has loads of bonds, strong covalent bonds that requires loads of energy to break them bonds apart. And so silicon dioxide, a little bit like the closest, I suppose, the structure is very similar to diamond. It has this massive structure, and anything that's like that, as you may have known from year 1 chemistry, your giant covalents take a large amount of energy because they've got many strong covalent bonds that require loads of energy to break. Okay, meanwhile, the other two, phosphorus and silicon oxide, so phosphorus pentoxide, which is P4O10, and sulfur dioxide, so remember, not looking at the sulfur trioxide example here, just the dioxide, and they form simple molecular structures. They don't have this giant covalent structure or macromolecular structure that we've seen before, and as a consequence, the only thing which holds these molecules together are weak intermolecular forces, and because they're weak intermolecular forces, it means that less energy is actually required to break these bonds in comparison to your macromolecular structure of silicon dioxide. Okay. So let's have a look at some of these these ionic oxides. Okay, so these are remember, your ionic ones are metal and non-metal. So these are going to be substances like sodium and magnesium that we're going to be looking at, and actually these form alkaline solutions when we add them to water. So you can see that our ionic oxides, they contain the O2- ion that accepts protons from the water molecules when it's actually dissolved in solution. Okay, so it accepts the protons when dissolved in the solution. Obviously, it then forms your water. So let's have a look. So we've got sodium oxide, So your sodium oxide reacting with water, as you can see there, that will form a sodium hydroxide, which is obviously our alkaline solution. Now, sodium hydroxide, as you may have seen in the acid base topic in year one, in topic 1, so in the physical chemistry section, then you'll know that sodium hydroxide is a strong base. And because it's a strong base, it actually readily dissolves in solution. It has no problems at all. And as a consequence, because it's very soluble, it's the pH is going to be quite high. So it's going to be somewhere between 12 and 14. So sodium hydroxide is a strong base. You've got to be very careful with sodium hydroxide. On the other hand, magnesium hydroxide, it doesn't dissolve very well in water. And because it doesn't dissolve very well, then in fact we don't get much magnesium hydroxide actually being produced, and the magnesium hydroxide doesn't split up very readily because it's not very soluble, nowhere near as soluble as sodium hydroxide, and so therefore we don't get many OH minus ions in solution, and so therefore it's nowhere near as basic. So the pH is probably going to be somewhere around 9 to 10 with magnesium hydroxide than compared to with sodium hydroxide. But you can see the reactions are the same. So we've got sodium oxide, magnesium oxide, both reacting with water and both produce hydroxide. It's just one is more soluble than the other. Okay, so let's look at, there's our ionic oxides. So now we're going to look at some simple covalent oxides. So remember our simple covalent molecules, remember from the previous slide, these are compounds that have, for example, your sulfur and your phosphorus oxides. And so actually when we dissolve these in water, these form acidic solutions. So remember, ionic oxides formed basic solutions. Your simple covalent oxides are actually formed from non-metals such as phosphorus and sulfur. So you can see your simple covalent oxides form acids to form solutions with a pH of 0 to 2. Okay, and this is assuming a minimum concentration of moles per 1 mole per dm cubed. That's the minimum concentration we're looking at. So let's look at our phosphorus oxide, so phosphorus pentoxide. This forms phosphoric acid. Okay, so you can see here's our P4O10, so phosphorus pentoxide, which is here, reacting with 6 lots of water, and that will form H3PO4. Now this is our phosphoric acid, which is here. Now phosphoric acid actually breaks down into 3 H pluses and PO4 2 minus. So this is a triprotic acid, so it produces 3 protons per phosphoric acid molecule. So you can see here this is clearly forming an acid, as you can see. And so the acids formed, like I say, they dissociate, forming your H plus ions, and so forming the H plus ions and negative ions, and these are known as conjugate bases. But what you need to know really here is that the phosphoric acid, when it's formed, dissociates and forms the H plus ions. Okay, so let's look at the sulfurous one. Sulfurous acid or sulfuric acid, should we say. Now your sulfur dioxide, so remember this, your sulfur dioxide reacts with water. It actually happens in 2 steps here. Reacts with water and it forms H2SO3. Now H2SO3 is sulfuric 4 acid or sulfurous acid. Do not get this confused with sulfuric acid, which is H2SO4. Okay, so it reacts in 2 steps. So you've got here SO2, sulfur dioxide, forming sulfurous acid. Sulfurous acid does dissociate to form 2H plus and SO3 2 minus. So because it's forming H plus ions, then this is these substances form acidic compounds, as you can see on there. Okay, so let's look at how you make sulfuric acid then. Well, remember sulfurous oxides actually form 2 main types of oxides. That's sulfur dioxide, which is SO2, but to make sulfuric acid, we need to use sulfur trioxide, which is SO3. That's the main difference. Still reacting it with water, and we form sulfuric acid, or also known as sulfuric 6 acid, because the oxidation state of sulfur is +6. And you can see there that our sulfuric acid There it is. Okay, so our sulfuric acid actually dissociates to form 2H plus and SO4 2-. So both of them are still producing H plus ions. It's just our sulfuric acid is actually made using sulfur trioxide, and sulfur dioxide is made using this. You must be able to distinguish the difference. So look out in the question, see if they're giving you sulfur dioxide or if they're giving you sulfur trioxide, and that will determine what type of acid you actually produce. Okay, sulfur is a little bit of an odd one because it does form two main oxide products, as you can see there. Okay, so let's look at the other two, which were silicon and aluminium oxide. So we haven't obviously left them out either. These actually behave differently when we add them to water, and this is why we've kind of put them to one side. So we've looked at our sodium and magnesium oxides when we add them to water, and we've looked at a phosphorus and sulfur. So now we're going to look at silicon and aluminium, which are the ones in the middle. Now they're a little bit strange, so let's look at silicon dioxide first. This forms giant covalent structures. So remember that from what we mentioned previously. So they have loads of strong covalent bonds. It requires loads of energy to actually break these, and for this reason, silicon dioxide is insoluble in water, and it will react with a base to form a salt. So it's actually classed as an acid, but in terms of the addition to water, it doesn't dissolve, so therefore it won't form a soluble, won't form an acidic solution or a basic solution as we've seen with the other lot. Now, think about it. Silicon dioxide is the main structure of sand. So if you put sand into water, it doesn't dissolve. Thankfully, there are no beaches left. But you can see here, this is the reason why sulfur dioxide doesn't form acidic or basic solutions. But we do class it, like I say, we can class silicon dioxide as an acid because it will react with the base to form salt. So it's technically an acid, but it's just insoluble in water. And aluminium oxide is actually something called what we call amphoteric. So that means that it's actually behaves both as an acid and a base, so it has both characters. Now remember, aluminium oxide has some ionic and covalent character in there, so it's mainly ionic, but it has some covalent character in there, and so this means it is insoluble in water. So if you add a bit like silicon dioxide, aluminium oxide is insoluble. It doesn't dissolve readily because of some of this covalent character that it displays. Okay, so let's look at some acid-base reactions. So we're going to look at, obviously we've looked at the period 3 oxides and how they dissolve in water and do they form acidic or basic solutions. But what we need to know now is the period 3 oxides, how do they actually react with an acid or a base? Okay, so we need to know all these reactions. So like I say, the period 3 oxides react with acids and bases according to the standard equation. So remember, acid plus base gives salt plus water. Classic equation that you need to be aware of. Okay, so let's have a look at the reactions involving some basic oxides here first, shall we? So let's start with magnesium oxide being a metal oxide. It will behave as a base, remember, okay? Because remember, when we added it to water, it will form a basic solution. So we react this with an acid, and we form our salt, which is magnesium chloride, which is there, plus water. No different there, okay? So let's look at sodium as well, because sodium is obviously our other metal oxide. So sodium, here we're going to use sodium oxide, of course. Reacting it with an acid here, we're going to use sulfuric acid. It could be hydrochloric. You've got to be prepared to write down the salts and the name of the salts. So this one's going to be sodium sulfate, as you can see here. And obviously we're producing water as well. So all of them are producing the same pattern, okay? So let's have a look at how these reactions look for acidic oxides. So let's look at silicon. Remember, silicon, although it's insoluble in water, it does react with acids to produce salt and water. So here we are. So we've got sodium hydroxide as a base, and that's going to react with silicon dioxide. That's it. So that's going to react with silicon dioxide, which is this structure here, and that's going to form our salt, sodium salt, and we're going to form H2O as well on the back of that. So similar process here, similar type of reaction. Acid plus base gives salt plus water. There's nothing really too tricky about this in terms of in terms of knowing, what the formulas are, because we know there's a standard structure, which is acid plus base gives salt plus water. Okay, so let's have a look at another one. Let's look at phosphorus pentoxide, so P4O10. Okay, we're going to react that with a base such as sodium hydroxide. So have a look at the similarities here with this type of reaction. Again, we're forming our salt plus water. So remember, your salts are formed from the metal of the base and the non-metal here, which is in this case is the PO4 bit, for the actual in the acid element. This one's a little bit more trickier because you've got PO4 here. It's always going to be a phosphate. This is sodium phosphate here. It's always going to be a phosphate because we're using phosphoric acid. So your salt's always going to end in phosphate, but the metal really comes from your non-metal here. So this is sodium hydroxide, but if this is potassium hydroxide, clearly this would be K3PO4. So, you just adapt it to whatever base and acid you're using. Obviously, we produce water as well. Okay, so let's look at our sulfur oxide. So we're going to look at sulfur dioxide first, and then we'll look at sulfur trioxide, because clearly that's another example of an oxide. Sodium hydroxide react with sulfur dioxide, forms a sulfur. You've got your sulfur-based salt here, your sodium sulfate, okay, which is here, and then you've got water, and then sodium sulfate is here. Okay, so sodium sulfate has been formed. This is when we use SO3. All you really need to know is just look at the actual sulfur oxide reactants that you're using here. So you've got SO3, SO2, and just look at the name of look at the salt products that you're producing here. So Na2SO3, Na2SO4, which is used here, and so obviously that produces water as well. You just need to be able to write the equations down, okay, and be able to form the equations. You just need to be vigilant about the reagents that you're using. There's a lot of equations here, there is, but they're all following a similar structure, which is acid plus base gives salt plus water. Okay. So let's look at. So obviously these are we've looked at all of them. You'll notice there's one that's missing, and the one that's missing is aluminium oxide. So you can remember that what we mentioned before is that aluminium oxide actually has an amphoteric nature. So that means it actually acts as an acid and a base. So we need to kind of isolate this one and do it separately. So let's look at how aluminium oxide reacts with sodium hydroxide. In other words, acting as an acid. So this is acting as an acid, and it will form your salt. Now notice you form an aluminium salt here. This is your salt. There's no water produced, so this is a little bit unusual. All we are literally doing is adding everything here and writing it into one salt. Okay, so you've got to remember that there's no water produced when aluminium oxide is reacting with a base when it's acting as an acid. Okay, so let's have a look at the aluminium oxide. This time is reacting with an acid. So you can see here, aluminium oxide's acting as a base here. This is the acid here. This is going to form a salt and water. This one does form salt and water. So you form an aluminium sulfate, which is here. And obviously 3 molecules of water as well. So you can see here, there's loads of equations here. But the key thing is just knowing acid plus base gives salt plus water. Okay. So you need to know them reactions. Apart from aluminium oxide is the only exception when it reacts with the base and it just forms a salt. That's the only exception you need to know. Obviously, we need to know which ones are soluble in water and do they form acidic or basic solutions. So you've got to remember that. And we've got to know how these period 3 elements, how do they actually react to form the oxides in the first place. So that was towards the start. And also, just a very final point, critical point, is sulfurous oxides. It's a bit of an exception. It forms 2 different types of products. You've got sulfur dioxide and sulfur trioxide. So as long as you remember that, and obviously you need to know the explanations behind the bonding side of it as to what their structure and bonding, as to explain the melting points of these substances as well. So that's quite important for that. Okay, and so that's it. Told you it was quite a relatively short video. So that's everything on properties of period 3 elements and their oxides. It's definitely period 3, not group 2, what I was saying before. Obviously, you've got to be able to compare and contrast them all. So Yes, so that's everything on period 3 element oxides. There elements in the oxides. There is loads of videos on here for AQA year 1 and year 2 chemistry. The full range is available at Allery Chemistry. They're all for free. There's whiteboard tutorials on there and exam workthroughs as well. There's loads of information on there. Go and fill your boots. All I ask is that you hit the subscribe button, and that will be fantastic. There's no, like I said, these are all for free, so the subscribe button is critical there. So just hit that, and that will be brilliant, absolutely fantastic. Also, if you do want to purchase these, remember the link is in the description box below. But that's it. Bye bye.